Hello again, and welcome to our microelectronics course, and we will be continuing our bipolar junction transistor. As you remember, we did two parts until now, and we will be continuing our third part. So, in this part, we will be discussing more details about our bipolar junction transistor. So, okay, we can skip this part, and we will have to pass on a recap. So, if you still remember what we did last time, we did our the three we did the three BGT configurations. So when we say BGT, we are talking about the bipolar junction transistor. So we have the common collector and the common emitter and the common base. So it is either a common collector or a common emitter or a common base. So the common terminal is common between input and output. So when we say a common terminal is the common between the input and the output. So you have a common between the input and the output. So when we say a common collector, the collector is a common between the input and the output, and so for the others. So let's have the next part is the different, or we mentioned before, configuration the different configuration. So there is a different input or output characteristics, and of course a different applications. So if you remember, we did a lot of configurations, and each configuration has its own characteristics. So let's talk about these configurations. And we have the configurations characteristics. So for, of course, we have the characteristics and the configuration. So the configuration, it could be a common emitter, common base, or a common collector. As a first characteristics, we have the circuit diagram, how it looks. We have our terminals. We have our input current, our input voltage, output current and output voltage, and finally the factor of current amplifications. So for the common emitter, our base is the input, while our collector is the output. And as it is a common emitter, our emitter is the common. Then we have our common base. In our common base, the base is the common, the emitter is the input, and the collector is the output. While the common collector, the collector is the common, the base is the input, and the emitter is the output. About the input characteristics, since the base is the input, so it is an EB, since in the common emitter, while in the part here when the emitter is the input, so our IE is our IE is our input current, while here we have the base, so it is basically as well as an EB. Okay, the input voltage here is between the common emitter and the base and the input. So it is an input voltage, so it be between the common and the input. So we have our VBE, and we have also our VBE, and here we have our VBC or VCB. Okay, about the output current, since the collector is the output in the common emitter, we have our IC, and same for here, and same for here. So since the output is the emitter, so the IE emitter is the current output in the common collector configuration. and the voltages is just the same as the output voltages is the same principle. So we have our VCE, our VCB, and VCE, while the factor of the current amplifications is basically IC. In the common emitter, we have our alpha, which is the IC over IE, while the beta is the IC over IB, and the gamma, which is IE over IB. So that was a recap on the configurations and its characteristics. Let's continue in our recap. So to continue in our configurations characteristics, we have the characteristics and the configuration. So if we want to mention the input impedance, it is in the common emitter, it is moderate, so it is basically less than 1 kilo ohm, while in the common base it is very low, which is less than 100 ohm, and in the common collector configuration it is high, while the output impedance in the common emitter it's also moderate and high, while in the common base it is very high, but in the common collector it is low, and so on for the other characteristics. You can read them on and you will have your recap here. Okay, so now it's the big question. Hello again, and let's continue our microelectronic course, and we will be talking about the what is biasing. So what is biasing? Okay, so if you have any idea, you can write it down, or you can simply ask ChatGPT. And the second question is how to select the operating point. So how we can select the operating point in the Q, the Q point, I would say. So biasing, yeah, that's the word, biasing. So what do we mean by that? Transistors are used in a wide variety of applications in a different configurations. We know that. So transistors used variety applications and different configurations. Okay, to use this bipolar junction transistors in any kind of application, it is necessary, so the use of BJT in applications, it is necessary to provide sufficient voltage supply. Of course, provide sufficient voltage supply. But the voltage supply could be more important here. So the voltage supply and a current. And current to what? For what? To turn on the transistor and to operate in the active region. So we have an active region and reverse regions and so on. We will be talking more about them in a few minutes. So let's repeat this again. To use the BGT in any kind of application, it is necessary to provide sufficient voltage supply and a current to turn on the transistor and to operate in the active region of the transfer characteristics. And this process is called biasing. So applying or providing sufficient voltage supply and current in order to turn on the transistor and operate in the active region of the transfer characteristics, and everything here is called biasing. So biasing is basically provides sufficient voltage and current to the transistor, more or less. But yeah, let's see in details. So biasing is providing a fixed minimum amount of current which will flow through the transistor with the desired fixed voltage. So is providing a fixed minimum. So remember, we have a fixed minimum amount of what? Amount of current. So we have current, just as here, and which would flow through the transistor. Okay, that's the goal. Flow through the transistor with the desired fixed voltage. We have our fixed voltage as well. As much as we have fixed minimum amount of current, we will have a desired fixed voltage across the transistor junction. Sorry. So the question here, why is biasing is especially important in BGT based applications. So why it is important? Why is biasing is especially important in BGT based applications? Okay, let's continue to so we can answer this. So continuing in the biasing, when an AC signal is applied to a BGT based amplifier, the following is expected to happen. So when we have an AC signal is applied to a BGT based amplifier, the following is expected. So what is expected when an AC signal is applied to a BGT based amplifier? So first, during the positive half cycle, during the positive half cycle, of the signal, the BE junctions, so the B based emitter junction is going to be forward biased. So in the positive half cycle, the signal of the BE junction, so the signal of the BE junction is going to be forward biased. So it will be forward biased, resulting in current flowing from the emitter to the base. So resulting this in the positive half cycle, we will have a current flowing from the emitter to the base. Remember, from the emitter to the base, and then from the base, then from the emitter to the base, from the emitter from the base, then from the base to the collector. Okay, to the collector. Okay, let's continue. During the negative half cycle, now we are talking about the negative half cycle, not the positive half cycle. So during the negative half cycle of the signal, the BE junction, so the signal of BE junction is going to be reverse bias. So we have now a reverse bias resulting in not a current, but no current flowing in the circuit. So you have no current flowing in the circuit, and the signal is not going to be amplified. So not going to be amplified during the negative half cycle. So we have a positive half cycle, and we have a negative half cycle. In the positive half cycle, we have a current. After, of course, the BE junction is going to be forward biased. It's going to be forward biased, and we have a current flowing from the emitter to the base, then from the base to the collector. But in the negative half cycle, there is no BE there is no forward bias, or in other words, we have a reversed bias, and this will result in a no current flowing in the circuit. Okay, so to obtain now we will be talking about to obtain an amplification, or yeah, to obtain an amplification, the following conditions should be given. So, in order to have an amplifications, you must have the following conditions. So, what are those conditions? So, the EB junction should be properly forward biased. So, the EB junction, the emitter-based junction, should be forward biased, and the CB junction should be reverse biased. So the collector based should be reverse biased, and there should be a zero signal collector current. There should be zero signal collector current. So this is basically the three conditions. Maybe there is more, maybe there is, yeah, not less, but yeah, those are the base one in which you'll be able to obtain an amplification. All right. So the transistor biasing. The transistor biasing is the proper flow of a zero signal collector current. So it is the proper flow of a zero signal collector current and the maintenance of a proper voltage on the BE junctions. So we are in the BE junctions, and our transistor biasing is basically the proper flow. It is the flow, I would say. It is the flow of what? Of a zero signal collector current. So you have your collector current. So when you are talking about a zero signal collector current, and the maintenance of the voltage on the BE junction. So you are in your BE junctions and your zero signal collector current, you are talking basically about the transistor biasing. So we have, yeah, the second point, sorry, in order to produce a distortion-free output in an amplified signal, so you want to produce distortion-free distortion-free output in amplified signals. So you want distortion-free. You want no distortions in your output in your amplified signal. The supply voltage and the resistance in the circuits. So your supply voltage and your resistance in the circuit must be suitably chosen. So you have to choose your resistance. You have to choose the right resistance and proper supply voltage in term of proportional. So the third part, these voltages and resistance value represent a set of DC voltages VCE Q. So, and the current ICQ, where the transistor is operated in the active region. So your transistor is in the active regions, and yeah, in this point we will talk about this Q now. So they define the point at which the transistor operates. So this VCEQ and ICQ, this point is which the transistor operates, or I would say, yeah, this point is called the Q point or the operation point of what? Of our transistor for sure. And very important note, we should the selection of the operating point. Yeah, of course, the selection of the operating point. We will be talking about the operating point more in details. So, what do we mean? What do we mean by an operating point? So for starters, okay, so the transistor acts as an amplifier in the active region. So in the active region, our transistor acts as an amplifier, all right? So once the second point, once the DC conditions, are established, when an input signal is applied, of course, to what? To the circuit, or to the circuit, the base current, is going to vary based on the amplitude. So our base current is going to vary based on the amplitude of the signal. So we have an input signal. We should apply it as an input. Yeah, it's an input signal. It is applied to our circuit. The base current, so the EB here, the EB is going to vary based on the amplitude of the signal. So this input signal has an amplitude, and this amplitude will affect our base current. So and leads and lead an IC variation leading to a variation on the output signal. Okay, the third point. If the operating point is chosen to be near to the saturation region, the output signal could clip at the positive edge. So what do I mean by that? So if the operating point, so this is our operating point, is chosen to be near the saturation region. So when the operating point is chosen to be near the saturation point, the output signal could clip at the positive edge. Of course, this is textual, but the best way to know it is by a graph that we will be having a lot of graph next, so it's fine. So the fourth point, if the operating point is choosing to be near to the cutoff region, so if this operating point is chosen to be near to the cutoff region, not the saturation region, but the cutoff region, the output signal could clip at what? At the negative edge and not the positive edge. So when you have a saturation region, when your operation point is near to the saturation region, you will have a positive edge. But when your operating point is near, or is chosen to be near the cutoff region, you will have an output signal that clips at the negative edge. Sorry. So both selections are not very suitable for an amplification. So both, whether it is near the saturation region or near to the cutoff region, both not very suitable for our amplification. Okay, and the best place for the operation point will be in the center of the active region. So we have saturation region, cutoff region, and active region, and the best place for operating point will be the center for the active region. So this is our operating point in a graph form. So in this part, we'll be talking more about the saturation phase. But here we saturation region. But here we'll be talking more about the cutoff region. So in both graphs, we have our VCE, our voltage collector emitter, and our current of the collector. So I see in both cases, and for this one, we'll be talking about the cutoff region because the cutoff region is just right here, while the saturation region is just right here. So this is our saturation, our maximum, and here we have our the other way around. So for the for the for the point, the operating point where in the cutoff region is near, as we said, in the cutoff region is in the negative edge, as we can see, is near or clipped at the negative edge, while in the saturation, if you remember, in saturation region, it's clipped at the positive edge. So in both cases, we are not in an optimal conditions. So we are whether out or whether down or whether up. So that's just a small description of the graphs. But yeah, we will be seeing more in details. Okay, before that, or I would say the next part, after the small description of the graphs, we can talk about the load line analysis. So what do we mean by a load line analysis? So, okay, we can start with the common emitter amplifier because there will be different amplifiers. For example, our okay, this is the common emitter amplifier. Then we'll talk about, yeah, maybe others, but most likely no. Yeah, but yeah, it doesn't matter. So the first one that we will be starting with will be the common emitter amplifier. So as long as the common emitter, so the emitter will be our common here. So our E will be here. So our base is going to be here, and our collector will be here in the output. Our base will be in the input. So the circuit can be analyzed using the load line technique. Yeah, it is similar to the diode circuits. Yeah, it doesn't matter. So we will be applying our Kirchhoff voltage law. So in which loop? So if we took this loop, we will be having our VBB, let's take it this way. So it is negative, so we're going to put positive VBB plus V in because it's also negative, equal, or we can do just minus RB multiplied by EB and plus our potential here because it is, we are going to the positive through negative, so it should be a plus as well. Or if you want to put it in the other way, it will be VBB plus Vin minus RB IB minus VBE equal 0. And this one became somehow this one. So remember, this is your emitter, and here your base, and here your collector. Okay, this is our common emitter amplifier. Let's talk about it more in details. So, what do we have? What do we have here? So we will be analyzing we will be analyzing of our input circuit. So analyzing of the input circuit. So when IB equals 0, so based on the equation that we wrote, if you remember, so we said VBB plus plus V in equal RB IB plus VBE. So the analyzing. So let's analyze the input circuits. So we have the input circuit because this is our input circuit. So we have when IB equals 0, our this will be to 0, and our VBE will be too simply VBB plus Vin. So based on this, we have an intercept of the voltage axis. Okay, let's talk about this more in detail. So when VBE equals 0, as much as it is here, when VBE equals 0, yeah, we are done here. So we have our VBE equal to 0 this time, and this one is not 0. So we will have our IB equal VBB plus Vin over RB. So why we did this? So we can know the curve, So here, so we have our VBE and we have our IB, okay? So when this point or this value is when IB equal to 0. But this value is when our VBE equal to 0. So, sorry, we have our line here, our load line. So this is our load line, and this is our device characteristics. So, based, so it is giving that the slope is -1 over RB. Yeah, I know it could be you could be non-familiar with it, but look, if you did okay, so if we took this as an f, the function of VBE equal IB. So when we have this point minus this point, so we have our in the axis we have our VBB plus Vin over minus 0. This point minus this point and this point minus, so we have 0 minus VBB plus Vin over RB. So we will be dividing here. So we will have our VBB plus Vin over minus VBB plus Vin over RB. Of course, we're gonna multiply this by 1 on RB, by RB, and this plus RB. So we will have this, and sorry, I believe I made a mistake. Yep, I made a mistake. I'm supposed to do the opposite. Yeah, let's see. We are trying, we are learning anyway. So we do 2 points. So we're gonna choose this point and this point. So at this point, our f equal to 0 minus our f equal to 0 minus, sorry, so we're gonna take this point and this point. So in this point, our f equal to 0, but in this point, equal VBB plus Vin over RB. Okay, now we're gonna take this is the y. This is the y of the VBB equal to 0, but here it's different. Now we're gonna take the x's. So we have here our x, which is VBB plus Vin, minus the x here is 0. That's it. So we have our VBB, which is minus plus Vn over R, R what? RB, yeah, sorry, RB, multiplied by 1 over VBB plus Vn. Okay, yeah, because it's just this multiplied by 1 over this. So you will have this is going by this, and you will have in the end minus 1 over RB, which is our scope. This is how to find the scope of any equation. So this is our load line, our scope, but the device characteristics is taken by, I would say, I believe it's taken by measurement, I would say, yeah, but it doesn't matter for now. You just have to remember that your load line, how to analyze your common emitter amplifier. This is how to analyze it. So you take when EB equal to 0 and when VBE is equal to 0, sorry, and your scope. You choose your scope, and you can sketch your load line, and the device characteristic are either given or are either given or are either known somehow. So now we'll be talking about the key point. So the key point, our key point, occurs where our V in equal to 0. So let's see, what do we have here? So let's continue in our common emitter amplifier. Yeah, of course, we are always analyzing our input circuits. Remember, this is our input circuit. This is the input circuit. This is the input circuit. This is the input port. Okay. So let's continue. So the EB values are found at the intersection of the load line for each E in. So the EB values are found at the intersections of the load line for each E in. So since the AC input signal V in T, the instantaneous operating point varies around the key point as the input signal change. Okay, a lot of information, but yeah, we can find that. So here in this part, yeah, this one is look more like the ones we started with. So we are in the common emitter amplifier, and we will be analyzing the output circuit. Now I want to stay in the input circuit, okay? So the EB values are found in the intersection of the load line for each EN. So the EB values, so your EB values will be found at the intersection of the load line for each E in. So yeah, for now we don't have the E in, so we don't see an E in, but we know that it is the intersection. Okay, then the second part, since the AC input signal V in, since the V in dt, V in of t, sorry, the instantaneous operating point varies around the key point as the input signal changed. Yeah, it's tricky, but I believe we can go through it. So now we will be talking about the output, the output circuit. Let's do the analysis of the output circuit. So now we will be applying the Kirchhoff voltage law as much as we did so far. Yeah, if we want, yeah, we can go back to our circuits. And here we have RC, IC, VCC, and VCE. So we have only 3 mains. And they are written as follow. VCC VCC equal RC multiplied by RC plus VCE. So this will be our output load line equation. Okay, so of course, if we wanted to know, the same for this, when VCE equals 0, we put VCE equals 0, and we're gonna find out that, yeah, so no, when we put IC, sorry, when we put IC equal to 0, so this, when IC equal to 0, when IC equal to 0, VCC equal VCE. And when VCE equals 0, when VCE equals 0, EC, so we can put it. So here, sorry, let's take this down. Let's take this down. Let's put a normal color and thin color maybe. It's okay. So in this part is when EC equals 0, when EC equals 0, then you have your VCE equal VCC. And here, when your VCE equals 0, your IC equal VCC over RC, which is this one. Okay, so the AC component of the VCE is usually much larger. Okay, this is a note to put. So your AC component of your VCE is usually much larger. Okay, then larger than what? Then your Vin. So this is why you have your amplification. Okay, so since your AC component or your VCE is much larger than your V input, then you have an amplification, or I would say the amplification occurs. And the final note, or maybe the other note, the common emitter circuit is an inverting amplifier. So your common emitter circuit is an inverting amplifier. Yeah, put that in mind. So here we can say the common emitter amplifier is an inverting amplifier. Okay. Yeah, I believe we'll be talking about this. Okay, so how to realize the biasing for the BGT or different mode methods. Yeah, it's okay. I will take a small break and get back to you to talk more just about this one. So after digging down about what the inverting mean, so I need you to focus with me. So when we said we apply a small wave at the input, okay? So we are putting something in our input, because we are doing the input analysis. Yeah, at least. So when the input voltage increase a little, our transistor conducts more. Okay, so our collector, he is here, our collector current increases, which mean the voltage across the collector resistor, this is our collector resistor, increase. So the collector voltage, the collector voltage, the voltage, not the current, the voltage decrease. But when the input voltage decrease, not increase, decrease a little, the transistor will conduct less, so the our collector current will be decreasing, and the voltage across the resistor will eventually increase. So let's put it this way. When an input goes up, output goes down. But when the input goes down, the output goes up. This is basically what we mean. But in the meaning of the inversibility. So when we are saying an inverting amplifier, so we are having a kind of a shift. So we are having 180-degree phase shift between the input and the output. So the voltage gain is negative. So yeah, so the gain is always negative. So this basically what do we mean by the inverting in this part. Okay, so yeah, we will be moving to the next part. So what do we mean by, or I would say how to realize the biasing for the BGT as a first question. Sorry, how to realize the biasing of a BGT. And the second question is, what are the different methods for biasing? Okay, so we have first how to realize the biasing of a bipolar junction transistor, and the second question is, what's the different method for doing so? So, okay, we have our BGT DC biasing. So we have fixed bias. What do we mean by that? So we have a single resistor from the base to the supply. So you have one single resistor from the base to the supply. So for a DC analysis, capacitor can be replaced by an open circuit. Okay, so let's see this more in detail. So we have our fixed biased circuits. This is our fixed bias circuits. We have a resistor here, and we have our configuration. Our emitter is the as a common emitter. Our output is our VCE, and we have a second capacitor here as well. So, of course, we are going to do the DC equivalent, and it was mentioned that for the DC analysis, capacitors can be replaced by an open circuit due to, so this is our equation. So we have our IC is equal over 8BFC, which is going to infinity when the frequency equal to 0. Yeah, since we are in a DC analysis, our frequency is 0, and by definition, our IC, yeah, it has a name. I don't remember it, but yeah, we can find it later. And that's why we put our capacitors here, as an open circuit, and we can do our analysis. So we put it as 2 VCCs here instead of 1, and we keep up the other details. So continuing our BGT DC biasing analysis, let's talk about the the fixed bias. Yeah, we are in the fixed bias. We will be talking about the load line, sorry. So we have our line here. If you remember, we already discussed this scope. You can just check it again. Here we have our load line, and here is the device characteristics, and the scope is 1 minus 1 over RB. And for the IBE, for sure, in proportion with VBE, but for VICE, VCE, and EC is a bit different. And for each value of IB, there is a point. So, and and of course, that's the purpose from the as an output. This is our output because IC is in the output. Okay, so this is our output characteristics, and here is our input load line. Okay, let's continue. So our BGT DC biasing has the fixed biasing has some advantages. What those advantages? So we have a very simple biasing methods using a few number of components. If you remember, we used only two components, two capacitors. So we have two capacitors, or maybe three sometimes, but yeah, in this case, it's just two capacitors. So a very simple biasing methods using so simple biasing using few number of components. The second point is the operating point can be fixed anywhere. So your operating point, your operating point can be fixed anywhere in the active region, for sure, in the active region of the characteristics by selecting a suitable value of the resistance IB, because choosing the resistance will affect our IB, and by that we will have a multiple or I would say a changeable and modifiable operating point. And the last part is we have, yeah, when we say change in multiple and so on, this means a very high flexibility. Okay, but of course, as advantages, we have disadvantages. So our fixed bias method, I would say, have some disadvantages. What are those disadvantages? The gain depends on the DC value of a VBE. Yeah, so we know that the gain depends on the DC bias value of the VBE, the input voltage in the circuits as well, which is the input voltage in the circuits. Which mean when you have no input or whatever, or something happen in the input, then your biasing would not work. So in practice, it is not possible to set the bias value of the input voltage to the desired value. So in practice, in theory, yeah, it is possible, but in practice, it is not possible to set the bias value of the input voltage to the desired value. So yeah, it is not modifiable in practice as we thought. But yeah, so even if we could set the input bias as desired, and even if we put the input bias as desired, the device variation, we have the change in temperature, etc., or whatever. So this will cause the gain to change. So the gain will change. And finally, with a rise of temperature or change of resistor, our gain, yeah, will be changed. Yeah. And finally, so we need a better biasing method. Okay. So let's see. So now we will be talking about the emitter biasing. So we did the fixed bias. Now we will talk about the emitter biasing. Okay, just a quick learn here. So we have our fixed biasing. This is our fixed biasing, but it looks like this one is just the same as this one. But it's okay. Let's learn more. Let's learn more. So the emitter bias in the BGT DC biasing is as follow. So the DC bias network with an emitter resistor is used. So, all right, so that's the difference. We have an emitter resistance here. But here in the fixed bias, we don't have an emitter resistance here. Okay, so that's the difference. All right, so we said that the DC bias network with an emitter resistor is used. And the purpose of that is to improve stability or over the fixed bias. Reduce sensitivity to temperature. Okay, that's to reduce sensitivity to temperature somehow. And finally, or I would say the last point of this emitter resistor method is to reduce the parameter variation. So then the analysis of type of biasing is done by first we should examine the base emitter loop. So we have our base emitter loop. Then the collector emitter loop. So our collector emitter loop. Okay, so this is how the analysis of this method works. Okay, so let's start with the collector emitter loop. So we have our emitter bases. Yeah, but they say we should start by the base emitter loop. Why they went to the collector? Yeah, because it is most complicated maybe. But yeah, it's okay. So the collector emitter loop, we're gonna use the KVL analysis for the DC equivalent, and we will have our VCC minus RBIB. So VCC minus RBIB plus minus VBE and minus REIE. Okay, so we will also replace. So we have our function here. We have our equation here. Sorry. Then we should substitute the emitter current by this value. So we know that VE. So equal. Okay. So VE equal beta plus 1 multiplied by IB. So yeah, this is from somewhere else, but yeah, you can use to it and replace it here somehow. So there is a relationship between IE and IB. We know that, and between beta and IB and so on. But yeah, you can just use it as it is, or maybe we can search for it. What do you think? Yeah, I'm not gonna search for it right now, but yeah, just remember that VE equal beta plus 1 multiplied by IB. So you replace it wherever there is a VE or wherever there is, wherever there is a VE, okay. So our equation will be as follow. So we have our VCC minus VBE equal, we know that IBRB plus IERE. Okay, so at the IB multiplied by RB plus I'm gonna need to focus on this. So what do we have here? We have, so let's replace it again. So we have our IB RB plus IB RE beta plus 1. So where did this came from? So we know that the VBE and VC is okay. So we know that the IB and RB is okay. So here we have IERE. So we have somehow IERE. Sorry, yeah. IE multiplied by RE. So there is an RE here. RE here multiplied by IB multiplied by beta plus 1. Okay, so this is replacing IE and not the beta plus 1. Okay, so I need to check this before. Yeah, I don't need to check this. This is a mistake here. Yeah, this is an IE. Yeah, this is an IE. So yeah, that's making sense because yeah, the voltage cannot, because here we have a volt, and here this is neutral. This is just a number, doesn't have a dimension. Here we have an ampere. A voltage cannot equal an ampere unless it is multiplied by resistance. So here is an IE, not, not an, not an VE. So here we have your IE here. And when you replace it, that will make sense. Okay, I believe we corrected some small error here. Doesn't matter. But yeah, maybe it's just a small error, but it's okay. Then we can, we after replacing, we will have this equation, and based on this equation, we can select IB in the right in the left side and have our IB equations as follow. So, and from this, I believe they can draw the curve. Okay, not yet, but yeah, it's okay. So let's see now the uh, the base emitter loop. Okay, so yeah, we can continue. We can continue now. So this is our RE, IE. Yeah, we know IE equal beta plus 1. IE equal beta plus 1 IB. Okay, then we go to the base emitter loop. This is our emitter. Yeah, this is our emitter bias, and this is our base emitter loop. So the emitter resistor RE is reflected to the base circuit by a factor, yeah, beta plus 1. Okay, appearing much larger, and it appear much larger. So we know why beta plus 1, we already discussed that. So the IB will go through RB and RE, but multiplied by beta plus 1. Okay, so that's why we defined a new resistance, which is the RE. So this is an input resistance seen as the base, So beta plus 1 RE. And the equation shows how the RE stabilize the bias and provide a simple way to calculate IB. So IB will be easy to be calculated because we have only one current passing through this. And if they calculated already, yeah, no, they didn't. So this is the collector emitter loop. Yeah, it's okay. So this is the collector emitter, but this is the collector emitter loop. No, this is not the collector emitter loop. This is the base emitter loop. Yeah, this is the base emitter loop somehow. Why they put it as an... Yeah, that's something I don't understand, but yeah, it's okay. So this is our configuration. And this is our base. Yeah, this is our base and RE. This is base. So yeah, this is our base and our emitter. This is our base emitter loop. Why they put it as a collector loop? Yeah, it's okay. Anyway. So this is the small loop that we will have, the second one. And the final one is the collector emitter loop. So Yeah, the collector emitter loop. This makes sense. Yeah, a lot of mistakes. A lot of mistakes. A lot of mistakes from our beloved teacher. Maybe, yeah, I didn't enter the presentation. Maybe correct them. We can check them later. Okay, so this is when you use a KVL, it's going to be easy. You have RC multiplied by IC. We have minus VCC. Then we have plus REIE and plus VCE. And here we will consider as an IE is almost IC. And after replacing, we will have this equation. And based on this equation, we know that the emitter voltage is VE equal IERE, VC equal, VC equal VCC minus RCIC, or VC equal VCE plus VE. And we know what VE is. And the base voltage is as follow. VB equal VCC minus IBRB, or VB equal VBE plus VE. So you're wondering what is this? So VC, from this one, you can find all of these. So your VC, which is RCIC, your VC, equal your VCC minus ICRC, because IC is equal IC is equal IE, and somehow the RE, it will be negligible, or your VC equal your VCE plus your VE. Okay, so there is no one better than doing exercises to understand more. So what is the emitter bias advantages? The emitter bias advantages would be as follow. So we have a simple biasing concept, an excellent thermostability, and we have a reduced dependence on the operating point on the transistor gain. And finally, we have a simple design and implementation. So, and of course, there is disadvantages. There is a much disadvantages here. Even though there is a lot of mistakes, I believe, but it's okay. So we have more components than the other biasing. We have a power loss on the emitter resistor. Maybe it's negligible. And there is a reduced voltage gain due to the feedback resistor, reduced voltage gain, and requires higher supply voltages. Another optimized solution, two supply emitter biasing. So when you have a two supply emitter biasing, and you should apply negative supply VE on the emitter side, which we'll be discussing now in the voltage divider bias and more in details. Okay. We will back to this in a few minutes. So now we will be talking about the voltage divider bias. Okay, so always in our BGT DC biasing, and now is the voltage divider bias. So we have a two resistor, R1 and R2, from a voltage divider to set the base voltage. Okay, so this is our base voltage. So we have our R1 and R2. And this type of biasing is used to minimize or eliminate dependence on our beta. So that's the goal, or I would say, it's to minimize or eliminate dependence on beta. So with a proper circuit design, ICQ, or the operating point of IC, and our VCQ remain nearly constant. So now we are talking. So it's nearly constant, while the IBQ change with beta. Okay, so let's see some calculation. So we are in the, we are always in the voltage divider bias, and we were talking about the exact analysis, or analysis in general. So we will be doing the Tivna equation. So a Tivna equation is applied to the input side of the base. Yeah. So here is the Tivna circuits. So from this we want to have something like, it is not here, but we want something like R E Tivna, the E Tivna, and the R Tivna. So based from this circuits, the E Tivna equal VCC over multiplied by R1 over R1 plus R2, and the R-Tivna equal to R1 in parallel with R2. So of course we already, that's it. And so let's put it down. So it will be something like this. So it will be something like this and this. Okay, so all right, so here we have our B, here we have our A, and here we are our VBE, and here we have an RE multiplied by E. And we already know RE, and we know that this is the RE multiplied by EE, and we know that IE could be replaced by beta plus 1 IB. So let's continue our lovely equations. So and of course this one is R Thivna multiplied by IB minus plus beta plus IB. So when we do the KVL here, we will have something like this. So we will have our A Thivna minus minus, or this will be, let's put it this way. So we have a minus plus, so, and we take this one, and here we have minus R Tivna multiplied by IB, and then we have minus VBE, so minus VBE, then is a minus RE multiplied by IE, or directly IB or beta plus 1. So let's change the color, and let's put this here. Okay, so we're gonna put this part together. So this part together, and the other part in the other side. So we will have E Tivna minus VBE equal R Tivna IB minus RE IB beta plus 1. So when we we can continue. So we have A Tivna minus VBE equal IB multiplied by R Tivna minus, R Tivna minus RE multiplied by beta plus 1. And when you take beta in the by itself, so you divide by this part, and you will have in the end this equation. So this is the origin of this equation. This is where this equation came from. So once IB is known, other current and voltages are calculated. So for example, our VC can be calculated as follow. Okay, and yeah, so our VC is in the other side, but yeah, it's okay. Okay, let's continue our analysis. So this is our voltage divider bias, and since we know these equations, we can conclude the other one. So our VE will be our VB minus VBE, and our IE will be our VE divided by RE. So since the collector current is equal almost to the emitter current, and the final one, VCE, could be this equation, VCC minus IC multiplied by RC plus R1. The key point is independent of beta. So since, as you can see here, IC and VCE, there is no beta as a factor here, so that's why you can say that it is independent. Okay, so that was the analysis. It's not in detail, but it's okay. With the exercises, we can know more. So the voltage divider bias. What are the advantages here in our voltage divider bias? So this biasing provides a very high stabilization of the operation point. So we have a high stabilization in our operation point in a case of variation. In case of variation, the base voltage is fixed. So base voltage fixed by a resistor network. Okay. Thermal stability against temperature variations. So there is a thermal stability. There is a thermal stability against temperature variation. So against temperature variations. Then we have a reduced dependency on transistor gain. So you have reduced dependency on the transistor gain. So your beta is safe. And it's simple to design and implement, just like the one before. Okay, so the disadvantages. What are our disadvantages here? We have a more component required than other biasing. Yeah, it's simple to design, but there is more components. There is a power loss on the resistor network and the sensitivity to resistor tolerance. And finally, it requires a high supply voltage. Okay, so yeah, that's it. The next part is how to model a transistor and how to calculate transistor circuits. So let's say what we have here. So we are talking about the DC circuit models of the BGT. Okay, so we have our active region model. Which is the forward bias. So we have a forward bias. Okay. So for the NPN, when we have an IB superior than 0, VBE is almost equal to 0.7 volt, and our VCE is equal 0.2 volts. So here we have our NPN. This is how it looks like. So you have here your VBE. So here it is your VBE. Here you have your VCE. So here you have your VCE. And yeah, and your IB is superior than 0. Here it's the opposite. Your IB is inferior than 0. And your VCE is inferior than minus 0.2 volt. So here is your part here. And basically that's it. This is how it looked like. Okay, so the saturation region model. So put in mind, this is the active region model. Now we'll be talking about the saturation region model. So this is the saturation region model, how it look like. For an MPN, for the MPN, your VCE equal almost 0.2 volt. So your VCE is equal almost to 0.2 volt. IB remain positive, and the constraint for saturation is as follows. Beta IB is superior than IC, which is superior than 0. So it is the same for the MPN and the PNP. Okay, so, and finally, the cutoff region. The cutoff region is for both MPN and PNP. It is an open circuit between all terminals. Specific voltage constraint, define the cutoff. And with a forward bias up to 0.5 volt, currents remain negligible. So we have a cutoff model is still valid. Okay, and finally, yeah. So the final part. So you have your how-to. So DC circuit model of the BGT. Yes. So try and error approach to find the operating region of the BGT. So this is how to do our calculation. So let's read them. So try and error approach to find the operating region. So you want to find the operating region. Okay, choose one of the 3 BGT operation regions. So whether the saturation, with the cutoff, or the active region. Analyze the circuit to determine IC, IB, and VBE and VCE by using the transistor model. So we need to use the transistor model for the region chosen. Each region chosen has its own transistor model. Then we need to check to see if the constraint for the chosen region are met. So for example, for our VBE is inferior than 0.5 volt for the cutoff mode. We already know that. And which beta IB, yes, beta IC for the saturation mode, and all this information for the cutoff mode, for the active mode, sorry. And if the constraints are met, the analysis is completed. If not, return to step 1 and choose a different region. Okay, we know that, yeah. So now we have the small signal models for the BGTs. So the base current given by, this is the base current, IB equal IBQ plus IB of T. Similarly, our VBE equal VBQ plus VBE. So IB to the T, which is the bigger B here, is given by the Shockley equation. Okay, this is the Shockley equation. We already discussed this before. One is negligible if the BGT is in the active mode. So remember, one could be taken off if it is in the active mode. Therefore, IB to the T equal 1 minus alpha. Yeah, so just the one is taken, and when we replace the bigger B with this equation and our VBE with this equation, we will have this equation. And after that, we know that, yeah, our IBQ equal, yeah, so it will just, we will just, okay, so how did we move from this to this? So, okay. Yes. So, yes, we know this. So, based on this, so we know that. So, when we replace this, we see this IB of the T, this IB of the T. We need to replace it by this one. Sorry, by where is it? 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 Yeah, no, sorry. The bigger one that we already know can be placed here, so in this part, and that's why in the end this part will be taken and we will remain only this. So let me explain this. So yes, this part here, which is this one, 1 minus alpha IES exponential, is simply IB of Q. That's why it is here. Okay, so this is your final equation, or at least what you are looking for. Okay, so so let's continue. So since VB e to the t is a small signal, the following mathematical approximation holds. So your exponential of the VBT over VT equal almost 1 plus VBE over VT. So you're going to replace it in your equation here, and you're going to end up with this equation. And from this, you're going to define a new function equal r to the p equal vt over ibq. And you're going to define, oh yeah, of course, you're going to take the ib to the t equal vb to the e, vbe to the t over rp. And we can put down that that rp equal v to the t over ibq, which is beta v to the t over icq. Yeah, of course, now you're just gonna have to remember it, but the best way is to do an exercise about it, or you can go to the physics. Okay, so that was this lecture, which is the final part of the BGTs. The next one will be something else, but that's it. Okay, see you next time.